Video course on textile engineering and technology.
Key methods to evaluate the opening and cleaning action in cotton processing.
Dr. Yehia Elmogahzy is the founder and the president of Learning LLC, a consulting education organization.
Professor Emeritus at Auburn University, Alabama, USA. Former Dean of Science, Technology, Math, Engineering at Ocean County College, New Jersey. A visiting professor at a number of universities including Rowan University, Keene University, and Montclair University, New Jersey, USA.
So far we discussed bale openers or pre-opening and the blending equipment. Now keep in mind that the blending aspect here is not so great. The essence of the bale openers is to block tufts, okay? Now if you're using a classic bale openers, yes, you have a great deal of blending. But also if you're using an automatic bale opener, you have a blending of the different tufts. But as we will see later on, the true blending happens later on as the fibers flow from one stage of processing to another. The second type of equipment that we will discuss is the opening and the cleaning equipment. And then after that, we'll move to the fiber mixing equipment. Opening and the cleaning equipment. Well, the main objective of opening is to reduce the tuft size to smaller size. We mentioned that in the principle. Even under conditions where the fiber stock is pure and clean, you have to do opening. Some people think that we open so it will be easier to dust off the trash. Well, we do opening in synthetic fibers, in polyester and nylon and all types of fibers, because as I said before, the high density bale has to be opened into smaller tufts and smaller layers to be able to eventually convert it into a linear fiber strand. So opening is an essential issue. Cleaning, on the other hand, is only associated with some fibers, such as cotton fibers, because of the trash particles in the fibers. So as we will see later on in the design of opening and the cleaning line, some lines will have no cleaning equipment by virtue of the fact that they are not processing cotton. Others will have it, and when you have cotton and the polyester blended together, then you have a problem there, because you basically have to have different channels, especially if you're doing some intimate blending in the early process, where the channel that takes the polyester down the stream of processing will have opening units, but it will have no cleaning units, while the channel that takes the cotton down the stream of processing will have both opening and cleaning units. Here we see the reduction of the tuft size down to smaller tufts, and simultaneously we have the cleaning process. And again, both opening and the cleaning are done simultaneously as a result of dividing and redividing the tufts, exposing the trash particles, and in the early process, if those trash particles are heavy, they will be removed by gravity or by the centrifugal force in the opening and the cleaning units. Later on, where we have larger penetration through the fibers, the principle of centrifugal force will be more superior in this case to eliminate trash or fine trash from cotton. The opening action. Well, in today's technology, the opening action is accomplished using different mechanisms. First, the mechanical impact. That is the mechanical impact through acceleration and deceleration of the fiber tufts against pen cylinders. This is very much like dusting the fibers all the time, okay? Or beating the fibers. In fact, I can replace this term here, mechanical impact, by beating action, okay, as we classically learned how to understand the opening and the cleaning line. We call this a mechanical impact, okay, and the term impact here is very important. That is beating the fibers so that any trash articles can be removed by gravity, and as you beat the fibers, you tend to separate them, divide them, and re-divide them. Secondly, mechanical penetration through the fiber tufts. Quite often you have to penetrate through the fibers. So it's not just a dusting from outside, but also a penetration, and that is for applying more fine or medium to fine type of opening and separation or dividing of tufts. Or progressive centrifugal action. And of course you can have the three mechanisms together. You can have the mechanical impact, mechanical penetration, and progressive centrifugal action. The point I'm trying to make here is these are the basic components of an opening action, and they are also the basic components of cleaning action. Cleaning is performed as through a continuous extraction of the trash particles, and centrifugal force here, as I mentioned a minute ago, is extremely important. You have to have some form of centrifugal forces to be able to dust away the trash particles. But there are also other mechanical components that we will see shortly, such as the mote knives, stripper or stripping rollers, and suction hoods to prevent really trash from going back to the cotton stock. Because yes, centrifugal action would be great for initial separation, But as long as those trash particles, especially the very fine one, are flying around the cotton, they will have a tendency to be reinserted into the fiber stock. So as a result of that, we need some other supporting accessories. And as I said, moot knives, suction hoods, all of these are very useful. Modern tools, by the way, because in the good old fashioned, we relied so much on the gravity by centrifugal force and the grid bars settings, which are the bars under the cleaning roller for the trash fibers to go through. But now we have more accessories to allow efficient cleaning. In a typical opening and the carding line, the tuft size is reduced by about 95%. So you can just imagine from the fiber layer that we take out of the bale using the automatic bale opener or the classic bale opener, there is a further reduction in the tuft size as you go to the end of the opening line, going into the carding line of about 95%. We're shooting for 100% size reduction, the card whip, but the minimum in most modern machinery is 95% reduction in the tuft size, and that's of course by weight for some of you who may be concerned about that. So from the first opening unit to the final opening unit, there is a reduction in tuft size that may range from 95% to 100%. And when we say the final opening unit, really, we mean by that the carding process. I tend to think of the carding process as part of the opening and the cleaning line. The reason we separate it in our discussion is because of its unique features and because of the fact that it is the first strand forming process, the carded slifer, as we will discuss shortly. As I mentioned, I cannot emphasize enough the significance of the opening action. The small tuft size is a key issue in achieving a homogeneous fiber blend. If you're doing 100% cotton, you must always evaluate your opening action. If you're doing a mix of cottons coming from different countries, for example, where bales are more than likely to have or exhibit different density, perhaps different height, perhaps different sizes, then again, this is a must issue. The evaluation of the openability of your process. Yes, there are a lot of machine makers recommendations that a textile technologist can follow. But keep in mind that most machine makers perform a limited experimentation on their laboratory. They are very reliable, yet they are not dealing with the same cotton you're dealing with. They are not dealing with the same environment you're dealing with. Certainly, they try to idealize their research and their experimental trials, and they give you guidelines that come from idealized experimental setup. You have to do your own homework when it comes to evaluating different machinery. And evaluation of the opening action is a very simple process. As I said, we reduce the size of the tufts by a range from 95 to 100%. That is the common. Now, what your process is doing may be different. You may have a very high humidity level in your operation that takes away some of that reduction. You're trying to open and divide and redivide the tufts, but the fibers are highly resistant to this opening action by virtue of the clinging power between the fibers resulting from high humidity, for example. So you have to be aware of this by continuously evaluating your opening units. The experiment is very simple. If you want to evaluate the opening unit performance or the openability, all what you need a card can, and you have a can of a constant dimensions, and the idea here is we need to dump a constant volume of fiber in this can. So before opening, we have the fibers put in this can, and also after opening. And the idea here is to determine what I would call the opening index. And opening index is the volume divided by the weight. So if this is a constant volume can, you're going to dump the fibers. You don't want to press the fibers. You just want to put it as is. No pressure, no compacting, no pressing on the fiber layer. Just as soon as you get the fibers out of the opening unit, dump it in the can, and keep dumping it without much pressure. The only pressure there would be, of course, the layer's own weight. And as soon as you fill up the can, you wait. And now you have the volume of the can, which is a constant, divided by the weight of the can. And obviously, a better opening unit will have a larger volume per weight, meaning a smaller tuft size. Here is an example. You have an opening unit, okay, and you have a cylinder of constant volume, and you dump the fibers, as you can see here, without any pressure, and then you weigh the can, and you have the mass of the can, and of course you account for the empty can and all of that, and you can do that before and after opening. And obviously, as expected, before opening, the mass of the fibers inside this can exhibits high density, meaning more fibers per unit volume, while here after opening you have much less volume or less density, and the difference between the two can give you an excellent indication of the opening index. M1, which is the higher, minus M2 divided by M1 times 100 will give you the so-called degree of relative opening. Why are we doing all of this? It's because the initial opening of the process is extremely important in achieving not only a homogeneous blend as a result of the smaller tuft size and the fluffiness of the cotton, but it may also reveal some problem. As I said before, if you have high humidity in your opening and the cleaning line, more than likely this will affect the opening performance of the fibers, and then you can anticipate a great deal of problem down the chain of processing in carding and drawing and of course in spinning, which will be reflected in ends down and the machine failures and the machine stops. And it's better that you make such an evaluation early on in the process so you can do something about it. It's also very important to discuss the concept of stepwise opening. In this graph, the horizontal axis represent the units. So this is unit 1, unit 2, unit 3, and so on, as you can imagine. These are the opening and the cleaning unit. So we're really talking about a stepwise type analysis here, where the fibers are fed in the first unit, they come out and then go to the next unit, and provided that you have accessibility to the fibers after each unit. And of course there are many experimental ways by which you can have fibers from the airstream or the pipes. And the vertical axis here represent the tuft size, okay? And as you can see here, and as we mentioned before, the idea is to achieve gradual opening, okay? As a result of that, you really cannot do this. This is a very sharp opening or a very sharp reduction of tuft size. As you can see here from the first unit to the second unit, you have an extreme reduction in the tuft size, and that's the last you want to do, because what does that mean? Major fiber damage or major crushing of some of the heavy trash, which will make it very, very difficult to remove in later processes. So it's very important to avoid steep opening. Now, on the other hand, you don't want to do this, because what this is a very slow process here, okay? That's what we call a drain or overworked opening, meaning you use so many units. That's going to the other extreme. So you can 100% make sure that you have a very slow, gradual opening. Obviously, this is not an economical way to do it. In addition to that, more units in the line. So you really have to be somewhere in the middle. And this is an issue that you can definitely consult the machine maker in that. The design of the opening and the cleaning line is primarily based on the stepwise opening approach, where in a design of any opening line, you try to avoid steep opening, and you try to avoid drain opening. So you try to really make the tuft size reduce gradually in a smooth process. Obviously, this concept here is directly related to what I mentioned before, which is the openability index, or the relative openability, which is based on the simple measure that I said, a constant volume can, and you dump the fibers in before and after. That will give you a measure of the relative openability, and it will give you a good indication of whether you are doing a steep opening or drain opening or somewhere in between. So please consider this simple experiment in your facility. Now we move on to the other action, which is the cleaning action. As I mentioned before, both opening and the cleaning are simultaneously done. As you open the fibers, as you divide the tufts and redivide them, a great deal of trash are exposed. We also mentioned the other mechanisms, in addition to the beating, the mechanical penetration and the centrifugal force. So we're now about to discuss again some technological tips that will allow you as a textile technologist or as a spinner to evaluate your cleaning action during processing. Again, the rule of thumb is large trash are easy to remove by virtue of their weight, by virtue of their gravity, by virtue of their ease of exposure, while small trash are extremely difficult to remove by virtue of their impedance into the fiber bulk. If you crush a large trash to a very small size, then that large trash will become as small in some cases as the fibers, or it will become powder. And if it is powder, that means it will totally entangle with the fibers, and of course the machine will be blind in this case of segregating the trash from the fibers, and you will see those very fine trash particles all the way in the yarn and in the fabric. So again, or as a result of this, the cleaning action, just like the opening action, will have to be gradual. So why we do an opening action in gradual fashion? We do that because we have to avoid fiber damage. Okay? Steep cleaning action will result in major fiber damage or excessive short fibers. Okay? A drain, we know the problem of that. An optimum opening action will result in optimum fiber damage or minimum fiber damage, and as a result of that you will avoid breaking fiber. The reason we have to do gradual cleaning action is very simple. We first have to get rid of the heavy trash, the large trash particles in the early process, which are easy to remove, and more importantly, we don't want to crush them, because if we crush them into smaller trash, it would be difficult to remove those small trash later on because of the entanglement aspect that I mentioned. So as a result of that, we start with mild cleaning, where we remove the larger trash first, and as we break down those big tufts into smaller tufts, then we'll be ready to remove the fine trash particles. How we go about analyzing or evaluating the cleaning performance, there are standard ways to do that. Here is the input material going into a cleaning machine, and here is the output material. Obviously the input material has trash in it, and the output material will have some residual trash. Obviously most of the trash has gone during the cleaning action. So we have three components we have to deal with here. The input trash content, the output trash content and the trash in the waste material. Unfortunately, the waste material will have fibers in it, right? And it will also have trash particles. And one would hope that most of the waste material will have trash. Ideally speaking, one would hope that all waste through the cleaning unit consists of trash particles and not fibers. And if you have fibers, one would hope that those fibers are not long, useful fibers that you could have used. Waste management. So again, we have input material with a certain trash level. We have output material with much less trash level as a result of the cleaning action. And we have waste material here that has fibers and trash. And obviously, the existence of fibers in the waste is inevitable. As long as you're doing cleaning using mechanical means, there is no way out of that. There is no such a system that would say, oops, this is fibers, we put it here, and this is trash, we put it there. There will always be combined. And the key issue here is you need to pay attention to your waste. Okay? The type of waste, the type of fibers in the waste, the percent of waste of trash versus fibers in the waste are all critical issues because they are cost related issues that you must take care of. Here is a very simple illustration of what we just said. Here is fiber in and trash in, which represent the total mass in. Here is fiber out and trash out, which represent the total mass going out. The waste will also consist of some fibers. As I said, we hope it's a small amount, and plenty of trash. So the trash and the fiber will give us the total amount of the waste. In this regard, we need to introduce some important standard terminologies that are used to describe and to characterize the cleaning performance. One is the cleaning efficiency. And the cleaning efficiency is an issue of waste, okay? Efficiency here implies how much trash in the waste, with an ideal efficiency of 100%. So the definition of cleaning efficiency is the trash in the waste divided by the total waste times 100. Very good. And obviously, in this case, a perfect cleaning efficiency would mean 100%. 100% means the trash in the waste is equal to the total waste, meaning there is no fiber in the waste. And that is great if this happens. Such a technology obviously does not exist. Okay? So you will always have some fibers in the trash, and if you're getting close to 100%, that means you have minimum fibers in the waste. Okay, the other extreme, of course, is zero cleaning efficiency, meaning zero trash, and obviously if it is zero trash, that means all the waste is fibers, and this situation does not exist either. So this is an equation with two extreme values that typically never exist in practice. You will never have 100% cleaning efficiency, okay, meaning waste that are consisting of pure trash, and you will never have zero cleaning efficiency. The value will be in between, and with modern cleaning equipment, the value of cleaning efficiency should be as close as possible to the perfect or the 100%. Now keep in mind that cleaning efficiency had to do with the waste. So if you want to analyze the cleaning efficiency, you really have to have access to the waste. And quite often this is difficult to do. In case of the opening in the cleaning line, you more likely will have an excess of the total waste of the entire opening and the cleaning line, because it is difficult to have waste from individual units. In the good old days, we used to have waste obtained from each cleaning unit. That doesn't mean that you cannot do that now, but it will involve more detailed experiment. The other definition or the other terminology we use to characterize the cleaning performance is the so-called cleaning intensity. The cleaning intensity, on the other hand, is easier to analyze because it deals with the input and the output, trash content. Indeed, here is our input, which will have fibers and trash. Here is our output, which will have fibers and trash. And the cleaning intensity is defined by the trash input minus the trash output divided by the trash input. Why we call it cleaning intensity? Well, let us imagine for a minute a cleaning intensity of 100. What does that mean? A cleaning intensity of 100 will be ideally great, because what does that mean? It will be all the trash out will be equal 0, which means what's coming out of the process will be pure, no trash whatsoever. This is practically impossible because, as I mentioned, in order to do cleaning we have to have mechanical action, impact, mechanical penetration, and centrifugal force. As long as you have units cover those wires, pins, or spikes, you are applying mechanical penetration through the fibers. So the only way you're going to have a 0 trash out, it would be if you clean the heck out of the fibers, if you intensely clean the fibers, and that will not be good because you have a trade-off to make, that is fiber damage. So you simply will never have a pure or a 0 trash out in any process. It is perfect, but is unrealistic, unattainable in practice. On the other hand, a 0 cleaning intensity, meaning the trash in is equal to the trash out, meaning the unit did not do any cleaning, right? Because if these two are equal, okay, that will give us a total cleaning intensity of 0, and again we will not call it a cleaning unit in this case. So again we have another extreme that is unattainable in practice. So just like the cleaning efficiency that falls between two extremes that are unrealistic, the cleaning intensity also have two extremes that are unattainable, and the best you can hope for is as close to 100 cleaning intensity as possible. That is a key issue here. Another important aspect of cleaning is the extent of fiber damage. There is a trade-off, as I mentioned. If you try to clean the fibers too much, and since we are using mechanical means to clean the fibers, then there is a great chance of damaging the fibers. Now, in general, damaging the fiber may take different shapes. Damaging fibers could involve losing elasticity of the fibers, or losing some of the mechanical properties of the fiber, and that's a detailed subject. But in practice, our index of fiber damage is always short fibers. Are we breaking fibers? That is a bottom line issue here. So if you have a cleaning machine, typically speaking, you will have some short fiber content in, okay? And as you remember, we define short fibers as the fibers, okay, that have less than or equal 0.5 inch length. And obviously, as we mentioned before, a fibers of a length of 0.5 or less is typically of much less use than the normal fibers. So that is our definition. That's the standard definition of short fiber content. You have short fiber content in, even in the bale coming to the opening and the cleaning line, as I mentioned before, and as you've seen in the clip, as a result of the lint cleaning during ginning, there is a good chance to find short fiber content that may range from 2-3% best case scenario all the way to 20% to 25% in some worst case scenario. So none of the machines will piece up the fibers back together. The only thing that these machines can make is to make it worse. That is, you feed in a fiber this way, and this machine here will, as a result of the mechanical action, break the fibers. And as it breaks the fibers, then the 1 inch becomes 2 halves, each of half an inch, perhaps 3 pieces. Okay, and that is what you want to avoid as a result of cleaning. And the only way to avoid that is by watching out for the cleaning intensity that we mentioned in the previous slide. Indeed, if you try to reach 100% cleaning intensity, you will break a long fiber like this into small pieces, and those small pieces will be absolutely useless in yarn quality or down the stream of processing. So you want to avoid all of that. So as a result, we can measure the short fiber content in, and here is short fiber content created by the machine, which are typically the short fiber content waste, because we have waste which will have fibers, as we mentioned before, and some of those fibers will be short. We would hope that most of them are short, but we will also have short fiber content out, that is going out on the other side of the machine. That is what I call the short fiber conservation rule. That means you have short fiber in and you have short fiber out. The short fiber out will be equal to the short fiber in, because nothing is going to happen about the short fiber in unless they are removed via waste and the short fiber created by the machine. So more than likely, short fiber content out will always be greater than short fiber machines in, unless of course a great deal of those short fibers were dumped in the waste, as we can see here. Okay, so you have to be aware of all of this. One way to calculate the extent of damage is to think a little bit about the short fiber content out. Because as I said, the short fiber content out may be a very highly variable parameter. Depending on how much fibers, short fibers that is, went to the waste, okay, the short fiber content out may be either greater than the short fiber content in, if minimum short fibers went to the waste, or in some cases they may be less. But being less, that does not mean that the machine did not break fibers. It simply means that some of those short fibers went into the waste. So we have to account for that, and that's really what this formula is saying, that the short fiber content out is equal to the short fiber content in plus or minus some factor times the short fiber content created by the machine, and that factor will depend whether some of those short fibers went to the waste or they purely went with the output. That leads us to a very important term that I've introduced in a paper years ago, which I called the extent of fiber damage. The extent of fiber damage, if you want to know how much damage created by your machine, that's cleaning machine or opening machines in that sense, because they both can break fibers, it is defined by the short fiber content out minus the short fiber content in divided by the short fiber content in. Now, this definition here is oversimplification, because as I said, the short fiber content out may indeed be less than the short fiber content in. By virtue of what? By virtue of the short fiber that went into the waste. As a result of that, we had to add a correction factor to measure or determine a more reliable extent of fiber damage. So here we have the short fiber content correction factor equal to the percent waste, that's the total waste of your machine, times the short fiber content in the waste minus the short fiber content out divided by the short fiber content in. So if you account for this index here, you can indeed measure a more reliable extent of fiber damage. Obviously, just like the cleaning efficiency we mentioned before, this requires analysis of the waste fibers. You can either do that in the opening and the cleaning line via taking waste from the entire opening and the cleaning line, or if you have the luxury of taking waste from different units, then that will be a more accurate approach to do it. Here is some examples. Here is a machine A, short fiber content in is 10%, short fiber content out is 12%. Okay, this machine has 5% waste. Okay, now as we look at this waste and analyze it using the perhaps the Shirley analyzer or the APHIS system, we find that in this waste we have 60% trash and we have 40% all short fibers. That's an ideal situation because definitely you're going to have some long fibers as well. If the trash amount is 60%, that is automatically the cleaning efficiency of this machine. Okay, now we have a short fiber in the waste of 40%. So we can now apply the extent of fiber damage equation with the correction. First, it is the short fiber content in out, the 12%, minus the short fiber content N, which is the 10, divided by the short fiber content N. Now this basically will give us 20%. Okay? But by adding the correction factors, which is the total waste percent, the 5%, times the percent of short fibers in the waste, minus the short fiber content out, divided by the short fiber content in, that will give us the actual extent of damage. That's 34%. And one can imagine here, if we ignore the correction factor, all of this together, then we're only going to get 20% extent damage, which is really a way underestimation of the true damage created by the machine. So one of the merits of using the correction factor is to give us a more reliable index of the extent of damage by the machine. Here is another example. You may very well look at the short fiber content in a machine and the short fiber content out and find them to be equal. If you're using the crude equation of in and out, then one can immediately conclude that there is no damage. But if you look closer to the waste, and if you have a 5% waste like the previous example, and you have the same amount of trash and the same amount of short fibers, then using the correction factor, because the first term will obviously be 0, that is the underestimation, then the correction factor adds to that 15%. So although the short fiber content out looks like the short fiber content in, but the extent of fiber damage is 15%, meaning one can put it roughly that we have an excess of 15% of short fibers resulting from the cleaning action by this machine. We move on now to another aspect, another characteristic that one has to consider in evaluating the opening and the cleaning performance. That is the so-called nib removal efficiency. Now nibs, as we mentioned in the previous sessions, are a bunch of fibers. Here they are, okay? But you see what I'm doing here. Those fibers are now going to be entangled together, okay? Forming a ball. And you can imagine having too many of these, okay, formed during the opening and the cleaning action. Indeed, it is inevitable. If you try to profile the opening and the cleaning line, and suppose this is unit 1 in the opening and the cleaning line, this is unit 2, this is unit 3, and so on. And this is the nips. Suppose we're talking about nips, nip count, or nips per gram, then it is inevitable for any opening and the cleaning line, no matter how modern it is, no matter how adjusted or optimized it is inevitable that the nips will increase as you go from one unit to the other. Every time you do cleaning and opening, you're more than likely going to form nips, as you can see here. So please keep that in mind. As a result of that, it's very important that we talk about the nib change. I call it here nib removal because it's commonly called the nib removal efficiency, and it's better used for carding machine that they remove nips, as we will see later on. But the definition of nip removal efficiency is very simple. It is the input nips per gram minus the output nips per gram divided by the input nips per gram. Okay? Now, if indeed the machine add nips, then the nip removal efficiency will be a negative value. If indeed the machine remove nips, then the nip removal efficiency will be a positive value. We see this in the opening and the cleaning line. Okay, so this is you're going to see in the opening and the cleaning line, while we see this in the carding unit.